Good afternoon. We are Group 11, and our senior project is on application and monitoring of ESPs. And my name is Benjamin Schwehm.
I'm Kelly Keane.
I'm John Michael Domingo.
And I'm Kevin Kovacic.
So for this presentation, we'll be going over our past completed action items. Then we'll give a little bit of a high-level overview of some of the technical information we've gained so far. And then we're going to go ahead and give our future action items to be accomplished. So far, what we've done, we've reached out to 2 industry contacts. We've reached out to Dwayne Lesmer, VP of Engineering for Access ESP. He'll be helping us on the application of the ESPs. And then our second one, Ben Dugas. He is a partner of Core Solutions, a branch of Shell, and he's going to be specializing in the monitoring of ESPs. We so far have completed our project charter and charter presentation, and we've also obtained some credible resources of ESPs to begin researching on the application and monitoring of ESPs. So far, we have completed all the boxes in yellow. We've looked over artificial lifts, we've looked over the application of ESPs, which involves conventional ESPs and also alternatively deployed ESPs. And in the future, we plan on looking at some case studies and some economic simulations for the alternatively deployed ESPs.
These are the methods of artificial lift that we've begun to research. They split up into 2 main categories, pumping and gas lift. With pumping, there's rodless pumping, which is an ESP, positive displacement pumps, hydraulic pumps, or jet pumps. And then there's also gas lift, which there's a continuous flow, which is a continuous injection of gas into the reservoir and intermittent flow. Deployed ESP methods are methods that were made to run ESPs without the use of a rig in order to save on costs. The first one was a cable suspended, which ran the unit on electrical cable through the tubing string. It was limited to shallow depths because of the cable strength. So to improve on that, they tried to create one run on coil tubing. The improvements were not very successful. Alternatively deployed ESP methods were created to run an ESP without a rig in order to save on cost. There's 2 different methods with the coil tubing. The first is led with the cable outside of the tubing string. And the other one has the cable run inside of the tubing string, which protects it and increases its lifespan. In addition to these 2, there is an inverted, which has the electric motor at the top. And you can also have the cable run inside or outside. These 4 pictures demonstrate the 4 different methods just to discuss. The first one is a conventional ESP with the cable run outside. The second one is with the cable run inside the coil tubing. And then there's the inverted ESP with the cable outside and the inverted ESP with the cable inside.
The second half of our presentation is going to be on the monitoring of ESPs. So far, we begin by researching some modern instrumentation and alarming methods. After this, we will branch out by finding gaps in current alarming and therefore attempt to implement new alarms to cover those gaps. Also, we will weigh the advantages and disadvantages of current alarms in order to improve these alarms for better efficiency. In addition to this, we will be gathering and analyzing real-world data in order to consider possible new alarms that we can implement.
Since an ESP's run life is largely dependent on the operator, it's important to regularly monitor them to ultimately save time, save money, and extend the life of the ESP. It's important to do these things to ultimately reduce shutdowns and startups, which are hard on the ESP and related equipment.
These are the 3 most important parameters to monitor for an ESP. The first one is the liquid production rate. Knowing the liquid production rate helps to determine whether the pump is operating on its performance curve or if it's fallen off track.
The second one is to measure the motor current from an ammeter chart. Differences in this reading can result in changes in the well, the pump, or the electrical system and are important to be tracked.
Also, a acoustic surveys, or well sounding, help to determine the annular liquid levels in the ESP. With this information, we can calculate the pump input pressure and then track that as well.
The graph below shows an important well with a functioning ESP. The ESP allows you to cover this difference in pressure to ultimately produce more liquid out of the well.
Over the years, ESP monitoring has evolved from the use of solely ammeter charts to gauge the current electric load to far more complex downhole measurements. The use of these downhole measurements are more expensive than electrical or acoustic methods, but the information gained is extremely useful and worthwhile. These advanced downhole measurements are continuously being implemented to a greater extent in offshore wells. These are examples of several parameters measured during advanced downhole monitoring. The four main types are current from the ESP, the pressure, temperature, and vibrations. The ability to see the various levels of each parameter is extremely beneficial in determining possible complications and what their causes are. As seen in this plot, starting and stopping ESPs greatly affects the discharge pressure and intake pressure, as well as other things such as the temperatures.
As our project advances, we will be using plots like this, using real-world data from our industry advisors to discover new trends and better applications for more reliable monitoring. These four instruments here, pressure, temperature, flow rate, and vibration transducers, are used in the monitoring of ESPs. They can be run individually or in packages in different configurations depending on which information is most needed. These are the 5 main causes of failure for an ESP. The first one we'll talk about is improper installation design. This comes from when you don't run in between your recommended liquid flow rate range for your pump. This accelerates pump wear very fast. The next one is faulty equipment. It's crucial to test equipment to be run downhole each time before it is. It's especially important when an ESP is included because of the hard startups and shutdowns. Thirdly, we have well conditions. There are many detrimental effects of equipment from well conditions. These include corrosion, scale formation, sand production in the pump, high well temperatures, formation gas, and high viscosity fluids.
Another cause of failure are electrical problems. These involve such things as voltage spikes, overheating of the ESP motor, and the presence of harmonics. Also, vibrations within the ESP can be detrimental to its use. Such vibrations occur when there's rubbing between moving parts and non-moving parts. This can throw off the rotation and cause imbalances, which could cause the ESP to fail. Also, these vibrations can wear out our bearings. We will dig more into vibrations later on in our project because it is one of the main forms of failures.
Here are some future action items we plan on accomplishing. Our first action item, we want to finish research on application and monitoring of ESPs. Our second future action item that we would like to complete is scheduling meetings with our industry advisors to get some hands-on experience. We want to set up a meeting with Dwayne so we can go over to Houston and visit his shop and actually see ESPs in person, and also be able to see their different applications. We would like to go to see Dan Dugas in New Orleans so he can show us some of the software used to monitor ESPs. Our last future action item will be to complete the project management plan and also complete the project management presentation. I hope you enjoyed our presentation. Until next time.